So the last thing in this section is properties of the definite integral. First thing I'm going to do is just kind of make us a list of properties. The first one, if you flip the limits of integration, it changes the sign of the integral. So the integral from b to a of f of x is equal to the negative of the integral from a to b of f of x. Okay. That makes sense, kind of. You're looking at the area under a curve. If you're going backwards, you get the negative of it. All righty. The integral from a to a of f of x is equal to 0 because delta x would be a minus a over the number of rectangles, and a minus a is 0. Here are some that just really make sense, letting us know that integrals work the way we want them to. This one, the integral from a to b of a constant times f of x is equal to the constant times b minus a. I left out my dx. So think about what a constant function looks like. It looks like a flat line. And you have a picture sitting right here. You have a flat line. What is the area underneath a flat line? It's a rectangle. What's the area of a rectangle? Length b minus a times the height in this case, which is c. So if you have just the integral of a constant, it's just the area of that rectangle. Number 4, if we have a sum, and I'm going to combine number 2 and number 4 here, and say that the integral from a to b of f of x plus or minus g of x is equal to the integral separately, f of x plus g of x. And finally, if we have a constant, we can pull it out in front. Okay, this kind of goes through why they work the way they do. And I'm going to go ahead and add this other property here to the end. If we have an area that's split into 2 pieces, we can add up the pieces to get the definite integral. So in this case, c lives somewhere between a and b. The integral from a to c plus the integral from c to b is equal to the integral from a to b. Okay, we'll look at an example of that in a moment, but I wanted to put all of our properties here together so we have a nice list of properties that we can use. Let's go ahead and take a look at example 6. So we have the integral from 0 to 1, 4 plus 3x squared dx. Now this depends upon something that we calculated in the last section, the fact that the integral from 0 to 1 of x squared is equal to 1/3. Without that, we couldn't calculate this at this point. After the next lesson, you could. So this integral is equal to the integral from 0 to 1 of 4 dx plus 3 times the integral from 0 to 1 of x squared dx. So the integral from 0 to 1 of this constant, 4 dx, is just 4 times b minus a. And then this is 3 times the integral from 0 to 1 of x squared. So 4 plus 1 is 5. Easy enough. So now we're going to use that last property, that if we divide pieces up, we can add them together. Okay, so this graph consists of 2 straight lines and a semicircle. If we want the integral from 0 to 2, of this function, that's just the area of that triangle that has height 4 and base 2. Yeah, not bad. Okay, so there's my triangle. So this one is equal to 1/2 of the base times the height, because here is where we go from 0 to 2. Now from 2 to 6, I have a semicircle. 2 to 6, g of x. Here we are below the x-axis. 4 lives in the middle. I'll make it work. So this is 2, 4, 6. So the radius is equal to 2. This area is going to be negative because it's below the x-axis. 1/2 the area of a circle, so half of pi times r squared. So negative 2 pi. So far we've just found the area under a curve. For part C, we want the integral all the way from 0 to 7. So that's the triangle and the semicircle and this little baby triangle over here. So I can divide it up, 0 to 2, plus the integral from 2 to 6, plus the integral from 6 to 7. I already know the integral from 0 to 2. It is, I never wrote down the answer, 2 times 2 times 4 is 4. 4 minus 2 pi. And then the integral from 6 to 7 is just that tiny little triangle. This is 1, 1, so plus, because it's above the x-axis, 1/2 of the base times the height, so 4.5 minus 2 pi, or 9/2 if you prefer the fraction. Okay, let's run through these last little practice problems using our properties. You should know the answer even before I get number 41 written down. because the upper limit and the lower limit are exactly the same. So it doesn't matter, even if that were something incredibly complicated in there, the integral is equal to 0. 42, they tell us that the integral from 0 to pi of sine to the 4th of theta d theta is equal to 3/8 of pi. We're supposed to figure out the integral from pi to 0 sine to the 4th theta d theta. So since we have flipped our limits of integration, that means this is the negative of the integral from 0 to pi. And I know I'm putting in lots of steps. You didn't have to put this step in. If this were a test question, you could have gone directly to negative 3/8 of pi and been done with it. And again, we're using the fact that the integral from 0 to 1 is equal to 1/3. I'm going to let you do this one on your own because we did one almost exactly like it. The last few properties of definite integrals have to do with one function being bigger than the other. If f is positive everywhere, then its integral will be positive from a to b. If f is always bigger than g, then the integral of f will be bigger than the integral of g. If you have a number that is smaller than f or a number that is bigger than f, then they bound the integral. And this kind of goes through and shows you what those look like. But I'll finish this problem up and the answer will be there for you to check when you do your class notes. You have the knowledge that you need for WebAssign.